Hi everyone. Today's lesson is going to be on the concept of what is the mole and how do we use it in chemistry. It is arguably the most important number that we're going to be using. It is what makes chemistry measurable for us in the lab, so it is a super important concept. So in this lesson, we are going to learn what is a mole and what is what we call Avogadro's number. How do we then use that number to interconvert moles to mass to particles for any elements that we could potentially look at? And then how do we name those particles that exist in chemistry? So is something an element? Is it a compound? Is it a molecule? And then how do we give answers with correct significant figures and correct labels? So these are all the things we're going to be talking about today. So the first concept that we really need to highlight here is going to be what is a mole. So a mole is nothing more than a unit of measurement, and it is exactly equal to 6.02 times 10 to the 23rd particles. So I want you to think of it like this. Have you ever heard of the term, skipped ahead. So a dozen is always equal to 12 things. So you always know that if you have a dozen eggs, you have 12 eggs. And if you have half a dozen eggs, you have 6 eggs. So in chemistry, we do something similar. Counting eggs individually is annoying to do, so we sell them in sets of 12. Same thing happens with particles. Particles are so tiny and so annoying to measure that we don't want to count them one by one. Just like when I buy eggs at the store, I don't want to buy them individually. I don't want to go to Giant and say, hello, can I purchase one egg? I'm going to buy them by the set of 12. Then I'm going to do the same thing with chemicals I'm going to count them by the mole. And remember, particles are so itsy bitsy tiny that 6.02 times 10 to the 23rd of them, which is like, I don't know, 602 sectillion, it's some crazy number like that. That is actually like something that we can work with in chemistry. Because when we look at like chemicals that we're utilizing, why can't I erase this? It's really difficult for us to measure it by the particles. So we measure it by the mole. So when we are looking at what do we call these particles? So we have specific terms. For elements, the smallest particle we see is what is called an atom. So that could be something like, let's say a zinc atom or an oxygen atom. So those are just the plain elements by themselves. We also see that we can have molecular compounds. These are things that are covalent. So those are what would be called a molecule, the smallest unit of something like water or something like, I don't know, sugar. Is going to be a molecule. So the smallest unit of sugar I could have, the smallest unit of water I could have is a molecule. And then for ionic compounds, that's where we're going to have a metal and a non-metal. These are, and I'm going to put that there, metal plus non-metal. These are what we'll see called a formula unit. So ionics get called formula units at their smallest individual smallest portion. So let's say we're looking at something like salt. The smallest particle of salt I could have is a formula unit. That's what we call it. So this number up here, that 6.02 times 10 to the 23rd particles, that is what we call Avogadro's number. So let's say I ask you, hey, I need you to get me 1 mole of zinc. Well, what that essentially means is it's 6.02 times 10 to the 23rd particles of zinc. So, the slide we were on, 1 mole is always equal to this conversion factor, 6.02 times 10 to the 23rd particles. And in this case, we're looking at an element. So that means it's an atom. Dozen. Oh gosh. How do we actually use this? This is going to be really helpful for us in trying to figure out how we can measure things in chemistry, in the lab. So let's look at an example, because this is where we're going to come back to what's called factor label. So if you forget factor label from part A of chemistry, it's essentially using conversion factors. So let's say we're looking at a football field, which is 100 yards long. Well, I know that 1 yard is the same thing as 3 feet. And I know also that 1 foot is the same as 12 inches. And I also know that in 1 inch, I have 2.5, what is it? Let me look it up quick. Centimeters in inches. Hold on. Okay, is 2.54. Sorry, I was unprepared there. So I can use these conversion factors. I can convert yards to feet, feet to inches, inches to centimeters, and figure out how big a football field is in centimeters. So factor label is nothing more than a tool for us to try to use this. So if I remember that 1 mole is equal to 6.02 times 10 to the 23rd particles, remember, that's just a conversion factor. Nothing different than 12 inches in a foot. So if I'm looking here, I have 2.50 moles of barium. What I'm going to be doing here and how I'm going to use that mole, that conversion factor, is by saying I have, oh, that's an eraser. I have 2.50 moles of barium. And I know from this conversion factor here that 1 mole of barium is 6.02 times 10 to the 23rd atoms. Okay, I remember that if I look back at this last, which you can see here. So what that is then equal to, if we multiply this out in our calculator, our answer is going to be 1.51 times 10 to the 24th atoms. Okay. And what we see here, I do want to keep in mind rules of significant figures. So I answered here with 3 significant figures because I had 3 significant figures here. I had 1, 2, 3, and 1, 2, 3. So I always want to make sure that those match when I am doing any kind of mathematical formula. So let's go on to the next one. Let's say now we're kind of going in the other direction. Now we're trying to figure out how many moles 5.0 times 10 to the 22nd water molecules are. So in this case, I'm going to do things a little bit differently. I'm going to start with what they've given me, which is the 5.0 times 10 to the 22nd molecules. And now I'm going to use this conversion factor up here. Now in this case, instead of the word particles, I see that it's the word molecules. So I'm just going to kind of scratch that out because it's the same conversion factor. So I know that there are 6.02 times 10 to the 23rd molecules in a mole, always. Doesn't matter what it is, there's always that many molecules in 1 mole. So now I'm going to divide by that Avogadro's number because it's in the bottom of that fraction doing this factor label. So now I have that many moles of water. Okay, so again, I'm just using this as a conversion factor to convert from one thing to another. Okay, so let's say I want to know how many atoms are in something that I can measure. Okay, well, I know that, 1 mole is always 6.02 times 10 to the 23rd atoms. But when I'm looking at something like copper, okay, I know that copper is an element on the periodic table, so I'm just going to quickly draw what that looks like. And you might notice that there's this number underneath, which is located here, and that is what we call the molar mass. What that number is how heavy in grams 1 mole of that substance is. So in the case of copper, if I said, hey, I need you to go get me a mole of copper, you would go back on a scale and you would weigh out 63.546 grams. That's how heavy 1 mole is of copper. And if you notice on the periodic table, no 2 elements, as far as I know, have the same molar mass. Okay, they might be similar to one another, but 1 mole, or 6.02 times 10 to the 23rd atoms, is going to weigh slightly different for each of the elements. And that's because each of the elements have different sized atoms. Some have more protons than others, which is going to make them heavier. So 1 mole of any element is going to be that molar mass, what we call the atomic mass. So it's molar mass, atomic mass, same situation, okay? So if we're looking at copper, again, it's going to be 63.54. If I was looking at something like, I don't know, let's say oxygen, for argument's sake, it would be 15.9994, okay? So that would be its atomic mass in grams per mole. okay? So that's how heavy a mole of oxygen would weigh. Oops, not what I wanted to click. Oh my heavens, what is happening? Okay, so let's continue this problem. Let's actually solve it out. I know that 1 mole of copper is always going to be 63.546 grams. And I also know that 1 mole of copper is always 6.02 times 10 to the 23rd atoms. So if I know how heavy that penny is, I know that it's 2.35 grams, I want to convert it to atoms. Now here's the deal. I can't do this in one step, okay? I can convert grams to moles, and I can convert moles to atoms, but I cannot do directly grams to atoms. I cannot do that conversion. I don't have a conversion factor that does that. So I have to use moles as the intermediate, okay? So that's going to be my middle step here. I always want to convert things to moles. So in this case, I know that I have 2.35 grams of copper, okay? And I know that the molar mass, so how many grams are in a mole, I know the molar mass is 63.546, okay? That's that atomic mass number. The reason why I wanted to put grams on the bottom here, okay? Oh, that's an eraser. The reason why I wanted to put grams on the bottom here is because I need to convert grams into moles, okay? So if I put grams on the bottom, grams crosses out, and I'm left with moles. That's my unit that's left behind. But they're asking me for atoms, okay? So I need to go an extra step. I need to convert moles into atoms. So let's look back up here at our 2 conversion factors that we have to do. I know that 1 mole is always equal to 6.02 times 10 to the 23rd atoms. So what that means is I can go through and convert grams to moles, and then moles to atoms. And that is what I need to do. Altogether, this is equal to 2.21 times 10 to the 22nd atoms of copper, okay? And again, I'm answering here with 3 significant figures because I had 1, 2, 3 significant figures here, okay? So this is a great example of how I need to use 2 steps in order to get my final product. What is going on? So let's try another one here together. It's another great example. In this case, I'm trying to figure out what is the mass. So that's going to be grams. And they're giving me 1.5 times 10 to the 24th atoms of gold, which is AU on the periodic table. So can I convert atoms into grams? Is there a conversion factor that exists for that? No. But what I can do is convert atoms to moles and then moles to grams. So that's what I'm going to do. I know that 1 mole of gold is always going to be 6.02 times 10 to the 23rd atoms. That's Avogadro's number, never changes. I also know on the periodic table, 1 mole of gold is 197 grams. So if I look up on the periodic table, I find gold, which is number 79. It's a big heavy molecule, or a big heavy atom. It's going to weigh 197, okay? So my first step is going to be converting atoms into moles. Then, once I do that step, I can convert it into grams, which is what I'm being asked for. So we're going to start with what we're given, 1.5 times 10 to the 24th atoms. We are going to convert atoms into moles, okay? So we're going to use this first step here. 1 mole is always equal to 6.02 times 10 to the 23rd atoms. So if I stopped right here, atoms would cross out, and the units that I would be left with would be moles. But I need to get to grams, so I have 1 more step to go. I'm going to try to convert moles into grams. So now I'm going to use my next conversion factor. Oh my, where's my Christmas list again? Sorry. So here on, okay, 1 mole is 197 grams, okay? So altogether, we're going to equal this out. Moles crosses out. Grams is the unit that's left behind. And the answer that we get is 490 grams. Now you might ask, why did we round it to 490? How come we didn't keep all the digits that were in the calculator? This answer needs 2 significant figures. So in your calculator, you might have gotten like 491, 492, something like that. But that's too many sig figs. In our original problem, we had 2 sig figs. So that means our answer here needs to have 2 sig figs. This 0 is not significant, okay? If I put a decimal point here, then it would be. But without that decimal point, this just has 2 sig figs, okay? So that's why I wanted to round down to 490. And let's try one more together just to make sure we're on the same page. So in this case, we have moles of lead and we're trying to find mass. So here, is there a conversion factor that gets me from moles to mass, to grams? Yeah, this is where we use the atomic mass. This is only one step, a nice, easy one. So I know that I have 1.65 moles of lead, and I know that in 1 mole of lead, it's always going to weigh 207.2 grams. I'm getting that from the periodic table. Why didn't I use Avogadro's number here? Well, I didn't need to, because I'm starting with moles, I'm starting in the middle, and I'm converting it into mass. So there's no need for me to use Avogadro's number here because it's just not necessary. I'm not working with any atoms at all. Starting with moles, going to mass. So moles crosses out, grams are left behind. The answer here is 342. Oh my heavens. 342 grams. Sorry for all of the pop-ups that are happening. I don't know what's going on. Okay, so there is our final answer. So I know this can be a lot, but hopefully by this point you at least know what is a mole, what do we call those particles for each of the species that we would see in chemistry, what exactly is Avogadro's number, and what does it have to do with a mole, and what does molar mass have to do with a mole? So how can they be utilized? And then how do we convert moles to mass to particles and vice versa? This is the big ticket item. So I'm telling you right now, like, you need to be able to do this. So if that means you're coming in and getting extra help with me, please do so, because this is very foundational in the rest of our course, okay? So please let me know if you need any help at all.